This is lecture 8C on the calculation of center of mass in one dimension. If there are more than two masses, more than two discrete masses, then x bar is just the sum over all the discrete masses times their distance to zero, or their x-coordinate, divided by the total mass of the system. For example, we could have M1 here, we could have an M2 out here, could have an M3 sitting here, could have an M4 over here, etc. This M1 is located at x1, we'll call this x2, x3, and x4. Then x bar, the center of mass of this system, you would add up all the masses, M1, M2, M3, and M4. Those make up the denominator. The numerator is M1, x1, M2, x2, M3 times x3, M4 times x4. This is all pretty simple if you have discrete masses and they're all located in one dimension, just located in a line. Now we're going to consider the situation which will lead to the calculus problem. Before that was simply a multiplication and division problem. Now we're going to look at the calculus problem. This occurs when the density is distributed. It's not located in little bricks, little separate objects. It's now distributed along the x-axis. For example, say I have the x-axis here, and this is my x equals 0, and say the mass, there's a little bit, let me give some red, so there's a little bit here, and then there's a whole bunch more here. As I go along, this kind of thins out, and then it gets thicker again, etc. Same thing over here, I could have it here, and then there's more mass right along in this area, and then there's less, so that it's not in discrete clumps where you can just add them up. Now what are you going to do? Okay, you have to calculate the mass all along this region. The density is required, and the density is given as a linear density. This is a one-dimensional problem, and it will be given as kilograms per meter. Right? And say you're going, wherever you're going from, say, minus 4 up to 10, then if rho L is constant, say rho L is 5 kilograms per meter, then the total mass would just be 5 times the length of wire that you have, in this case 5 times 14. We'd have 14 meters of wire. It's going to be in MKS units, and that just gives me 70. So 70 kilograms would be the total mass. If rho L is not constant, but instead varies, like I showed it here in red, then you must integrate. Okay, and here's the expression for it. We derived this before. We have to integrate, in this case, between minus 4 and 10 of rho L of x, the density, the linear density that varies with x, times dx, or integrate with respect to x. All right. To find the moment, we need to multiply each one of these by their location. Okay. We could do the usual, hack this up into little discrete sections. In each section, the density will be the density, representative density in this mesh, times delta x. Then we add up all these little masses for each little section. Take the limit as the number of section goes to infinity, and end up with the definite integral. In this case, it's going from minus 4 to 10. Okay, of x. Oh, I'm sorry, we needed that. That's the density. If I want the moment, I have to multiply by x. It's location x. Right. So this becomes a definite integral of x times density, linear density, possibly varying with x, dx. Then the center of the mass is this moment about x equals 0, this integral, divided by the total mass. Here's the expression you need for the one-dimensional center of mass calculation. You need an expression for the linear density in kilograms per meter. Right? It can be constant or it can vary with x. It appears under the integral sign right here. You multiply it by x and integrate. That gives you your moment about x equals 0. You divide by the total mass, which is the integral over the region of interest of the linear density. So here's an example. Let's say I have 10 meters of wire, and just for purposes of discussion, let's say that I've laid this wire down on my x-axis, on my coordinate system, my one-dimensional coordinate system, so that it's varying from x equals 0 to 10. And I have, there should be an L here. I have a linear density for this wire specified as 0.033 plus 0.05x. In other words, the density increases for some reason, either because the wire gets wider or because the composition of the materials in the wire changes. So it gets more dense as I move from 0 to x. Right? The total mass is the integral from 0 to 10 of rho L of x dx. That's the total mass. That will appear in the denominator of the center of mass calculation. And the numerator is the moment about x equals 0. And that is the integral from 0 to 10 of x times the density, the linear density, over from 0 to 10. And that gives me m0, which is the numerator. The total mass was 2.83. The moment about x equals 0 is 18.3. These are divided and gives me a location for the center of mass at 6.47. So the location of the center of mass, if I were to model this wire with its center of mass, would be about here at 6.47, and its total mass is 2.83, all located at this point, 6.47. That's a one-dimensional problem.